Well, before I start the presentation, I think I want to make a couple of comments on what I learned so far in these sessions. And that's interesting because, first of all, I think all of us has in the title or somewhere 3D printing concrete. But so far, only one person, Professor De Schutter from Ghent University, has showed some concrete stuff. Everybody else is mortar or cement-based. So that's a big problem. Since this session is about scaling up, I think that is one of the fundamental problems. And I know Liberato is laughing because I keep saying this every time I talk about 3D printing. And I will keep saying it because otherwise we are lying. You know? Our presentations are all lies. So that's one first comment. Second comment, another lie. We say that we do this because it's going to cost less. Well, the research from ASU shows that's not true. It's going to cost more. And the third lie is that we are doing this because it's environmentally better. That's not true again. We learned that's not true. So anyway, this is just for the benefit of what I learned in this session. By the way, excellent session. Now, the other thing that I want to mention, though, is since the topic of this session is upscaling, what do we really miss, and what, in my opinion, what do we really miss in addition to the things I mentioned earlier, which we do? And to me, it's modeling, is computational modeling. You know, Subu said, you know, we did a nice bridge, and my students didn't want to break it, right? And that's a good point, right? We don't have to do full-scale testing, right? That's, if we go there, it's going to be going back centuries where we would test structures at a large scale. So we should not do that. And then the other piece that is associated with this is, you know, we are at ACI, is codes, right? So there is a lot of discussion on how we codify and what are the requirements for 3D printing structure to really be legal. And if we follow what ACI has done in the last century, we are killing 3D printing of concrete, right? Specification-based codes are not the answer because we want to do topology optimization. We want to do all those geometries that are allowed by the non-existent of formwork. That's really the benefit. And so if we do that, you know, we cannot do a bunch of large-scale tests for shear strength, bending strength, whatever, and then fit curves. You know, we need to have material-level tests. We have to have predictive models that allow us to do the simulations at the larger scale. Okay, so that's, and so what are the things that we are doing at Northwestern in a project sponsored by the U.S. Army Corps of Engineers is try to develop an overall framework where we include a number of things all together. By the way, that's also because, again, the other things that Liberato mentioned in his presentation is that it's not just material behavior, it's not just material design, it's material design, process design, and structural design. And so we need to have a model that, or a computational framework better, that can allow all those phases of our design process, okay? And so the ambition of what we are doing at Northwestern is really to have this comprehensive computational framework that is allowed to us to simulate flow, right? Pumpability, extrudability, all that. Thixotropy, very important as far as buildability is concerned. But then also evolution of hydration and all the way to the hardening properties. Because eventually we need to have a structure that is hardened, and we need to know what is the strength of that structure. So I'm going to go over some of the things that we have done. We have not, of course, completed all of that, but we have made some progress. And for the fresh state, for the flow, what we have used is the so-called discrete fresh concrete model. You know, I built my entire career on repudiating continuum mechanics and doing all the models discrete. And so that's also for the fresh concrete, we do this discrete simulations. This model is going into the category of discrete element method or distinct element method approaches. In this case, it's just, you know, what you see in the yellow thing is one aggregate, and the external shell is cement paste. So we call it this hardcore soft shell type of approach. I'm not going to go through the equations other than mentioning that we try to formulate the model in terms of classical measure of strains and stresses so that we could have the model to be compatible to another model that I will show later, which is the lattice discrete particle model. That is the one that we use at hardened behavior. And so we want to have a formulation at the fresh state that is consistent mathematically throughout the entire life, and they can evolve naturally from the fresh state to the hardened state, as opposed to say, oh, at fresh state is a fluid, at the hardened state is a solid. Okay, when there is this change from fluid and solid, which is a fundamental, actually, scientific question, because the fluid behavior is quite different from the solid behavior. Okay, these are usual stuff. I think I'm going to skip. These are basically equilibrium equations, etc. The one thing I only want to mention on this slide is the effect of course, the rheology, and we define at the contact between particles. Of course, we can define a normal into shear component. We define an effective strain rate, and then we have an effective stress, and the viscosity is whatever that equation is. We can use Bingham. Actually, we typically use Bingham. Of course, you can use any nonlinear equation if you want to. That's not a problem. Okay, skipping this. I think these are just nice videos. Okay, now maybe go back to here. So this is some of the input information that we use for the model. And the one thing I want to mention is that, of course, the mixed design, so cement content, water to cementation, aggregate to cementation, maximum aggregate size, etc., those are all part of the formulation, because we'll try to recreate specifically that specific internal structure. And that is all the point of this type of techniques. This was implemented in Python scripts in FreeCAD. It's all open source, so whoever wants to get their hands on this stuff is there. We are using also as a solver Project Chrono that is, has already built-in methods for generating particle, controlling flow rate, shape of the outlet, and these type of things. There is a GUI. There is a GUI where you can put all the parameters, all that, and you get the geometry. Now, one comment about the parameter that govern the model. So first of all, we have this so-called mortar layer, the definition of this soft shell around the hard aggregate, right? And then you have some elastic property of the interface in the normal direction. As when it is completely fluid, we make the assumption that the material does not have shear stiffness. Okay, it's questionable. It's questionable, but that's exactly the evolution from fluid to solid, right? And then, of course, you have the viscous parameter, which is the yielding stress and the viscosity. Now, the mortar layer and that initial normal stiffness is what they govern compressibility of the fluid, right? Hence my question to Librad earlier. You do have some compressibility in the fluid, and that's important, actually. It's important in terms of how you capture the shape of the printed material. Okay. Now, this is just a very simple simulation of a slump test. Of course, this is the Project Chrono that we use. It's an implicit code, so you need to check time convergence, of course, right? And so you need to be careful. These are 4 simulations of the same thing for different 4 time steps. And at the beginning, the simulation seems okay, right? Non-symmetric, but okay. But in reality, it's just because you are far from the time convergence of your algorithm. So you need to be really careful. I know many people do, including myself, explicit calculation. In that case, of course, you don't have the problem of time convergence, but you have the problem of the computational cost. We did simulations of, I don't know if this runs. Oh, it does. This L-box test, of course, you can change the parameter and simulate self-compacting concrete, ordinary concrete, and then 3D printable, as you see in a second. Another simulation is shown here. Again, let's see if it runs. It does. Again, different behavior for different parameters that you can select in the model. And these are simulations of a building material cell or BMC test. It's a rheological test that we are using in the lab to characterize ultra-high performance concrete. That's the test, and here is the simulations that we can perform. And then, of course, we can compare the response in terms of torque versus rotation with experimental data. Now, one important aspect, so this is fresh concrete. Now, one important aspect is this thixotropy. Let me push everything up. And so what is thixotropy? Well, if you do a rheological test and you apply pre-shearing, you get a certain response. If instead you wait and you take the material at rest for a certain time and you do the same rheological test, you get a different response. So there is a flocculation and early structuration phenomena that occur in the material, which makes the resting period to be one important variable in the behavior. And that is very important for 3D printing. You know, 3D printing, typically there are two possible alternatives to make it a certain process buildable. And that is either we put hydration accelerators, right? So that it becomes hardened quickly. But then in that case, we have a problem at the interface. So you have very quickly we have cold joints. On the other hand, if you have a very long open time, then you don't have the hydration because at the beginning it doesn't start. And then you want to have the thixotropy to help so that the material is there and it has this additional strength that develops. Now, the typical model we found in the literature, and this was for many materials, including SEC, is a model like the one we see in the middle, where you have a certain lambda, which is an internal variable in this degree of flocculation. And then you have your Bingham model, for example, that is function on that lambda. And most of the time in the literature, they assume that the yielding strength is a function of the lambda, not the viscosity. And they typically use a linear dependence there. And the equation that you see at the bottom is the evolution equation for the degree of flocculation. Now, if you look at the SEC literature, you will see that typically that equation actually is used in two pieces, because the first term, which is the effect of the resting time, and the second, that is the effect of shearing, are at different time scales. Right? For 3D printing, that's not true. For 3D printing materials, you cannot decouple those two. So you need to integrate the entire equation for both the positive term and the negative term. Now, about the expression. The expressions that you see there, which is 1 over a power law and then a linear term in lambda, these are what is published right now. But we are verifying that this is not good for 3D printable materials. So certainly there is a lot of opportunity for researchers to work on that equations, and also to have more significant, well, more efficient way to get experiments so that we can verify that equation. Considering that degree of flocculation, as far as I know, and maybe I'm just ignorant, cannot be measured directly. Okay, so these are some of more additional comment on that equation. Again, on the left-hand side, also there's the exponents m, and also when t is omitted is the case where, again, SEC, where you just can decompose the equation. But the only thing that is important to this slide is the plot that you see on the right-hand side, because most of the model in the literature, they assume m equal to 0, meaning that they assume 1 over t to be constant, right, not dependent on lambda. Our experiments show that that's not, it doesn't work like that for at least for our 3D printable mix. So on the left-hand side are some force versus time for different shear rate. The shear history is up there. So it's 10 hertz and 3 hertz for 200 seconds. And if you use m equal to 0, you cannot fit them. You can fit one, but you don't fit the other. If our fitting of those data shows that m is 1. Okay, well, is 1 for everybody? No, that's for that concrete. But the bottom line is that the positive term of that evolution law is not constant, is dependent on the degree of calculation. And please tell me when I have to stop, okay? 2 minutes. Okay. All right, then I'll go here. So the other thing is that we really want to simulate this transition, okay? And so there are many different things that we need to do. Well, first of all, we now have a model for the fresh state. We have a model for the solid state, where we used it for the last 25 years. And now we have to make it the transition. Now, again, mathematically, the model are formulated so that mathematically you can transition, right? Now, computation is a different story, and also physical is a different story in terms of what does that mean, right? What does setting mean, right? And I've been asking questions even now in our committee. So what is setting? What is setting? Anyway, from the computational approach that we are taking is try to do this transition in this way. The other things that we are doing is scanning of those samples so that we can then recreate those samples in our computers and then test them. Okay, and that's again, it's for the hardened portion. As Shady mentioned, one of the work that we are doing is if I calibrate a model on my material on a cast set, cast specimen, can I use those parameters for the printed material, meaning that the difference is just geometry, or there is some intrinsic difference in materials? And we are trying to check that with these experiments, because now we have experiments for same material, cast in place and 3D printed, and we have the model that we can calibrate in one setting and using the other and see if we can capture the response. And that is what we are doing. I think I need to conclude here, and indeed, that's the last conclusion. You can read by yourself. But again, the message I have is we really need to invest much, much more on computational modeling of concrete. Now, this might be a self-serving comment, but I think it's really what I believe. And all the 3D printing companies that might be here, I don't know, they're probably, I think you guys should invest more in computation, because it's not sustainable to keep printing and breaking, printing and breaking, printing and breaking. Thank you very much.